This week we have a bit easier lesson, which is just polygons. Anyways, generally we classify polygons by the number of sides. Um, and just so you know, a polygon is just basically a general idea of a shape with only straight edges, and eventually it has to close on itself, and it can't do anything weird like this. It has so basically just a shape of that only has straight lines and none of the lines cross each other. And they're classified by the number of sides. So we have 3 as a triangle, 4 as a quadrilateral, 5 as a pentagon, 6 as a hexagon, 7 as a heptagon, 8 as an octagon, 9 as a nonagon, 10 as a decagon, 12 as a dodecagon, and if you have any polygon to the side, and it's sometimes generalized as an n-gon. It's not very precise wording, but occasionally they do it in contests if they don't want to tell you how many sides it is. Now, a regular polygon is something where all the side lengths are the same. So one example would be a square, where all these side lengths are the same and all of these angles are also the same. Another example would be a regular hexagon. Now, this is drawn very badly, but assume all these angles are all the same measure and all these sides are also the same length. And like I said, this isn't drawn to scale. I'm just bad at drawing. And the number of diagonals in any sort of n-gon, and as you recall, a diagonal is a line from here to here, a straight line from here to here, here to here, here to here. Basically, any lines connecting two vertexes except for the sides. Number of diagonals equals n times n minus 3 all over 2, where n is the number of sides. Now, the angles in a polygon, or in an n-gon, is equal to 180 degrees times n minus 2. Now, how do you prove this? Well, let's take pentagon, I guess. Now let's try dividing it into triangles. Now, as you see, there's 3 triangles here, or basically 5 minus 2 triangles, and as we've previously proven, the sum of all angles in a triangle, sum of angles in a triangle equals 180 degrees. And since there's 3 triangles, that means there's 3 times 180 degrees. Or we get back to this formula, and you can prove that with any sort of polygon, really. This is, let's see how many sides. 1, 2, 3, 4, 5, 6, 7 sides. We have 1 triangle, 2 triangles, 3 triangles, 4 triangles. Well, wait. 1, 2, 3, 4. Oh yeah, and also this 5th triangle here. I forgot to count that. So yeah, 7 minus 2 or 5 times 180 degrees. That's how many the sum of angles in a heptagon. Now you might be asking, wait a second, if it's about triangles, how come we can't split it like this or something? Then I guess that didn't really prove my point, does it? But we can probably split into a lot more triangles. Like, look, more triangles. Why can't we do that? Well, as you can see, like, some of these angles are really like sharing. And well, also, like these 3 might be 180, but then like this is also sharing with here, and that's not really an outside thing. So if you want to break down any sort of shape into triangles using this rule, they all have to like share a vertex, and all the other ones have to be on the edges, basically. You can't have any triangles where there's a vertex in the center and not on the edges. So now that we have this general rule, let's also prove the exterior angles of a polygon. Now the sum of all exterior angles in a polygon is 360 degrees. Now there is a way to prove this. So let's give you a shape this here. let's say that the interior angle is A and the exterior angle is B. Oh, and in case you don't know, exterior angles, basically if you keep on extending these all, the exterior angles would just be this angle, this angle, this angle, this angle, this angle. So all of those angles. So that means, let's say this is A1, B1. This is A2, B2, A3, B3, A4, B4, and this is A5, B5. Now, basically in general, A plus B will be equal to 180 degrees. And if you add up all the A's and B's, that means it'll eventually be, then we can say that if we add up all of them, that is equal to sum of A plus the sum of B. By the way, this like weird E looking thing, that just means sum. So it means you add all of them up. Now we know that the sum of the interior angles A, that's equal to 180 degrees times n minus 2. And then we have the sum of B. And then altogether, since there's n of these, that's equal to 180 degrees times n. Now, if you look, now we just move them all to one side, so the sum of B is equal to 180 n minus 180 n minus 2. You can simplify that to 2 times 180, or 360 degrees. So basically, for any sort of polygon, the sum of all the exterior angles is equal to 360 degrees, no matter how many sides it has. Now, let's talk about regular polygons. Now, like I said, in a regular polygon, four, five, six, seven. This is a badly drawn regular heptagon, but if it was drawn better, then all of these angles would be equal. And since you know that the sum of all interior angles is equal to 180 degrees times n minus 2, if we want to get any one of these angles here, that's just divided by n, because there's n of those angles, and the sum of them is equal to this according to the formula. And then the exterior angles of a regular n-gon, that's equal to 360 degrees divided by n. Now, an interesting property of regular polygons is that you can draw a circle that touches all of its points. So it can touch all of its vertices, and you can also draw a circle inscribed inside that touches all of its sides. And this is only for triangles. It can basically work for any sort of regular polygon where all sides are equal, all interior angles are the same. You can draw a circle inscribed inside or outside, touching all its vertices and all its sides. Now, let's talk about inscribed circles. Now, once again, this is kind of drawn badly, but bear with me. Okay, so we have what's supposed to be a regular hexagon, and it has a circle inscribed inside of it and a circle inscribed outside of it. And let's say that side of one of its lengths is L. And one thing is that these two circles are concentric, which means that they have the same center. Let's call it O. Now, how would we find the radius of these circles? Well, we know a few things, actually. We know this angle here. We also know that this side here, L. So L, that's equal to 1/2 L, where L is this little L is this side here, and big L is this entire side. And we also know the angle here because we know that it's equal to, if this is a regular polygon, that means it's equal to 180 n minus 2 divided by n, because that's the formula. And if we do that, we can say that if this angle, we'll call it theta, tan theta is equal to L over R, over little r, where little r is this one and big R is this one. And then we also say that sine theta is equal to L over big R because of the trigonometric ratios. We know this angle here. And also keep in mind that this here, angle theta, isn't necessarily equal to 180 times n minus 2 divided by n. It's actually 1/2 of that, because we split the angle in half here. So theta is equal to this over 2, basically. And now that we know the length of little r, the length of big R, we can also find the area of the circles. So we can say that area equals pi r squared. And if we want to find the area of the entire polygon, we can split this entire thing into right triangles. So if you look at here, we can basically split this into 2 right triangles for each of its sides. So then, since we know little l, we know r, presumably. So that means, well, one triangle is equal to one of the triangles is simply equal to 1/2 base times height, or L times R. And we can get rid of the 1/2 because there's 2 of them here with this full side. And then there are n of these, so it's equal to LRn. And since R is equal to L over tan theta, where theta is equal to this thing, that means just with one side we can figure out the area of the entire polygon as long as it's a regular polygon. Final thing I guess we can talk about is a regular hexagon, because for some reason math competitions love to use them. So if you have a regular hexagon, notice that you can split it into 6 triangles, and not just 6 triangles, but 6 equilateral triangles, because one of these angles in a regular hexagon is equal to 120 degrees, which means that this is 60, this is 60, and this is 60 degrees. So with one regular hexagon, you get 6 equilateral triangles. And then that means area is equal to 3s squared times square root of 2 all over 2, where s is equal to one of the side lengths. Anyways, that was basically today's lesson, and just to end things off, I'll give you an easy question. If you have a star like this, where let's imagine all of these sides, when I did this, all of these lines are equal, just try and find the angle, all of the interior angles. Anyways, have fun and see you next week.